Welcome everyone to the final lecture. Let me just share my screen and we can get going on this. Share screen. Okay, so this lecture is going to be broken up into three parts. First, I'm going to do a quick recap of the class. Then I'm going to talk about future classes that you might take. Hopefully this class has piqued your interest in AI. And then finally, I'm going to end with some broad remarks on where AI is going and what we should all keep in mind. So since it's a live lecture, feel free to interrupt and ask questions. I'll monitor the chat, or if Samara, if you notice anything, you can flag it to me as well. All right, so let's begin with a recap. So, congratulations to making it so far in the quarter. We've covered a lot of ground. So I'm just going to highlight some of the key things that you should kind of keep in mind. So recall, we started with this modeling inference learning paradigm. So modeling is the what. It's about how you build a mathematical model that approximates the real world. It might be a neural network, it might be a Bayesian network. Inference is the process of how you use the mathematical model to answer questions. It's trivial for neural networks, but can be really hard for Bayesian networks. And learning is how do you take data and produce a model so that you can do inference on it. So in this course, we talked about machine learning, then reflex-based models, state-based models, variable-based models, and logic. So let me just go through each of them in turn. So in machine learning, we presented the loss minimization framework, where you have a training set and you want to find parameters that minimize some loss. And one thing I want to stress is how general of a principle of this is. The loss captures basically kind of what you want a classifier to have. And we explored a few different types of losses depending on the task. And then we had a fairly simple algorithm, stochastic gradient descent, that was able to approximately optimize these objective functions. And this is really kind of the workhorse of machine learning. And these two slides, most of machine learning can be captured, at least these days, by writing down a loss function and kind of optimizing it. And it works for neural networks. It works for clustering problems and kind of k-means and so on. So I want to underscore that machine learning is kind of a general way of being. It's the idea of taking data and turning it into models, but there's multiple types of models. So we looked at reflex-based models in the very beginning, linear models, neural networks, nearest neighbors. Inference is just feed forward, pass through the neural network. And learning, we use stochastic gradient descent or k-means in the case of clustering. Then we looked at problems where you weren't interested in just a single decision, but you were interested in a sequence of decision from, let's say, from getting to point A to point B. And we embarked on a journey of state-based models. And here the idea of a state is a summary of all the past actions sufficient to choose future actions optimally. And that crisply encapsulates what kind of a state-based model is. And you have lots of practice coming up with state-based models for various problems. If they're deterministic, those are called search problems. You can use uniform cost search or A star. If you have randomness, you model them as Markov decision processes. You can use things like value iteration for inference. And for games, these capture the cases where there's an adversary and you have to use a min-max formulation. For search problems, we didn't really touch on learning, although you can do that. And for MDPs and games, we have these reinforcement learning algorithms. So really, you can think about reinforcement learning as machine learning for state-based models where there's randomness in the environment. Then we moved on to variable-based models, which is a higher level of abstraction. It's kind of a different modeling language, if you will. We looked at the key idea here is a factor graph, which captures a set of variables whose values you want to determine. And the factors, these little squares, captures dependencies between variables. And the key thing is that the factors are generally local, but the questions you want to answer are probably global. So they're deterministic. We have constraint satisfaction problems for things like scheduling. We looked at backtracking and beam search. If you put on your probability hat, then we can turn these factor graphs into Markov networks by defining a distribution over all the random variables. For inference, we looked at Gibbs sampling, but there's other methods as well. And then to give kind of a more of a interpretation to how the factors are constructed, we look at Bayesian networks where each of the factors was a local conditional probability. And then we look at forward, backward, and particle forking methods for at least chain structure Bayesian networks. There's much more to be said about here. This is just kind of a taste of variable-based models. For learning, we only look at learning for Bayesian networks based on the maximum likelihood principle, but you can apply maximum likelihood to any probabilistic model, including Markov networks. For Bayesian networks, it was really nice because learning as closed form, you just count and normalize. For latent variables models, you have the expectation maximization algorithm, where you have to use inference to impute the missing variables, and then you count and normalize. And finally, we looked at logic-based models. And here, the idea of logic is that it goes at kind of one level of abstraction higher. It introduces these things called formulas, which allows you to represent more kind of powerful things, even kind of infinite things. You can talk about like all the even numbers, for example, which is infinite set. We look at two models, propositional logic and first order logic, to do inference. It generally is pretty hard. For propositional logic, you can do model checking, or you can work on the inference rules directly, which is one of the nice things about having logical rules. Modus ponens and resolution are different inference methods. So sometimes I like to say kind of logic is about how you can express kind of very complicated things very succinctly. And learning, we didn't get a chance to talk about, but there are ways to also bring machine learning to logic. So hopefully this, you see CS221, and if you haven't seen a lot of this material for the first time, it can be a little bit overwhelming. There's just so many models, tools, methods. But I hope that this kind of organization gives you a way to think about, how everything fits together, right? I don't want you to think about like, oh, okay, there's nearest neighbors and there's Bayesian networks. How are they related? I want you guys to think about, this trajectory of, there's a bunch of models with different kind of, which are bucketed into reflex, state, and variable and logic. And then you can do learning on top of that. And that allows you to have just a much more nuanced and holistic picture of all the methods in AI. And what's important, I think, is that the individual methods, like whether you use particle filtering, will change over time. And generally in applications, you might have to use something a bit more sophisticated. So hopefully this class has imparted on you just kind of a way of thinking about the modeling and the inference and learning as separate, so that whenever you encounter a new algorithm that you read a paper somewhere, you can actually kind of incorporate it into your conceptual map. Okay, that's all I want to say about the recap. Are there any questions?
Can you throw some light on what should be the first tool that we should be using if we are presented with a problem? What's the tool that we should try first?
What is a tool that you should try first? It really depends on the problem. I think these days it's very natural and easy to throw machine learning, supervised classification at the problem. And that makes sense when your problem involves basically a single action, it's high dimensional, you don't really know what to do with it. But for many problems, like if you're kind of scheduling or doing route planning or something a bit more structured, you wouldn't want to necessarily start with machine learning, because in sort of start with machine learning, you need to gather data, and if you don't have data, then that might not be the best place to start. So I don't think that there's any one place to start. And hopefully you can think about the CS221 toolboxes like kind of the first layer in a breadth first search. These are the different options. You should think about, is machine learning good? Or should this be a search problem? Or should this be a Bayesian network, for example?
Okay. Yeah. Thank you.
Most of the current machine learning are reflex-based. They're a low-level intelligence compared to logic. Interesting point. We're in a very interesting time where a lot of what we see is machine learning. And it's also very impressive how a lot of the so-called reflex-based models are actually capable of doing some fairly sophisticated things. Like if you think about, AlphaGo, yes, there was multi-color tree search that allowed you to actually build a competitive agent, but even just like classifying a game board, that could definitely beat me at a Go. I think that, in cognitive science, people talk about system 1 and system 2, right? And both kind of coexist. System 1 is kind of the reflexive agent making kind of guesses at what should be the right thing to do, and system 2 is kind of the more rational, well thought out kind of reasoning path. And I think we need both, and the two need to kind of coexist and kind of feed off of each other. Could you give some examples of ML methods for search problems and logic problems? So search, a lot of things can be cast as search problems. So there's a whole field called structure prediction, which your goal is to output a structure, let's say a graph or a sentence or something. And in those cases, you often want to learn how to do that. So there you actually combine some search techniques. So the inference algorithm becomes search rather than just a feed forward through a neural network. But the learning part is still the same. And we didn't talk about the structure perception, I think, but it's you should look at it. I think it's in the slides still, where you are able to make a prediction using an inference algorithm. You get a prediction, you compare that with the correct prediction, and you do a gradient update. And then logic, there's similar things you can do. For example, Markov logic is a way of combining kind of Markov logic in the context of Markov networks, and Markov networks you can estimate using maximum likelihood. All right, great questions. Feel free to put more in the chat, but I'm going to move on for now since there's a few other things to get through. Okay, so now you've taken CS221. Maybe this was your first class. Maybe you've taken a bunch of other classes. I want to talk about what else is related to CS221. So first of all, I'm not going to give you a whole list of the complete list of courses. You can see the list of AI courses on this website, but that isn't even the whole list of courses which I think are relevant. So what I've done here is try to help us understand what are the types of courses that you might be interested in, why you might be interested in them. And then I'm going to go through each category and give a few examples of the most kind of popular ones. So the most kind of obvious type of course is, well, here we've taken 221, we learn about some methods. Let's learn more about some methods. Let's learn about Monte Carlo, Markov chain Monte Carlo in general, for example. And these tend to be more general purpose. But that's not the only type of course that I think is relevant. So applications are extremely useful. Of course, we are interested in applications because that's the kind of the real impact of AI is when they're applied to things. But also in the other direction, often when you take an applied class, you learn the method much better than if you take a kind of an abstract, because you appreciate when it works, when it doesn't work, all the nuances. And then finally, I would really stress and kind of invest in building depth for both kind of methods and applications. And usually these are courses not in AI. They might, for a method side, maybe investigating kind of more mathematical foundations, or in the applied area, if you're interested in computational biology, take a biology class. I think these days it's too, easy to kind of go through kind of an AI curriculum and not really have as much depth, because you can do a lot with kind of just downloading packages and running data. But I think if you really wanted to, especially if you think about kind of research, having the depth kind of can distinguish you from and make you more able to come up with kind of new insights and ideas. So let's start with methods. So these are categorized into maybe the different topic areas that we've covered in the class. So first is machine learning. Everyone probably knows about CS221. So it's kind of the standard poster child machine learning class. Compared to CS221, I think there's this question comes up a lot. It's more kind of mathematical derivations rather than as much programming. There's more continuous variables. CS221 tries to shield you from that and deal with discrete variables just for the interest of kind of scoping. And you learn some kind of fancier things like kernel methods and PCA. So if you really want to dig in more into machine learning, that's the class for you. If you are looking for just a kind of more of how do I apply machine learning, especially deep learning, which has been increasingly important, the TS230 will tell you how to train these deep neural networks, which has a lot of bells and whistles and things that you need to know about, like dropout and batch norm, to make these things work. So if you're really interested in the general practice of how you get deep learning to work, that's a class for you. So there's 3 other classes that I want to mention. Of course, there's more. So the first class is machine learning under distribution of shifts. So we have mentioned a few times that machine learning fails when the training distribution isn't the same as the test distribution. For example, there's adversarial examples, and this class is aimed at telling you, what's going on there and what you can do about it. Often you think about machine learning as kind of one task at a time, but increasingly now we're seeing much more general learning tools that allow you to generalize across multiple tasks. So that's pretty exciting. And finally, we think about machine learning often on kind of single data points, which are less structured, but machine learning can be done in the context of graphs. So there's a class about that as well. Then there's reinforcement learning. If you like the reinforcement learning section and want to know more advanced methods, take CS234. You get to learn about policy search, whereas we've looked at kind of more like Q learning, which is estimating a value function. Then there's decision making on uncertainty from the aeroastral department, which focuses more on model based. If you remember the distinction between model based and model free. So in kind of more serious applications, you really want to have maybe a model of what's going on in the world, and you could do things like planning rather than just like being a kind of a reflex agent. Generative models, if you enjoyed Bayesian networks and Markov networks, and this is the class for you. CS228, probabilistic graphical models. It's kind of a fairly kind of natural extension of the things that we've talked about, fancier inference algorithms, how you learn the structure and so on. In the last, I guess, 5 years, there's been a surge of interest in, generative models, which are supercharged with deep learning. And if you probably many people have seen GANs generating really photorealistic images. This is all enabled by deep generative models, which builds on the principles of generative models, but you kind of combine it with deep learning and you get, really interesting results. So let's talk a little bit about applications. I'm only going to talk about 3 applications: vision, language, and robotics. Of course, there's computational biology, there's healthcare, and there's other things which I'm not going to have time to mention. So vision, there's a kind of a stock, the canonical vision class is, I guess, at this point is CS231N. It's fairly machine learning heavy. You talk about like learn more confidence and transformers. So it's more general purpose than vision, but you talk about some vision specific tasks like detection, segmentation, generation. There is CS231A, which is more kind of on the vision side. So if you feel like you've already know your ML, but you really want to learn more about kind of vision, this might be a good class for you, because vision ultimately is about how light works in the kind of a 3D world, and so you kind of get into that. There's also I think a newish class on how AI intersects with graphics, which is kind of a close cousin of vision. And this has some emphasis on kind of generating things like generating animation, but also a much more in-depth emphasis on kind of rendering and geometry. Okay, so robotics. There's introduction to robotics where you learn about how you explore kind of physical models of robotics, how to kind of move arms and how to relate kind of joint angles to actually what the robot does in the real world. CS237 has a little bit more learning involved because for more complex robotics tasks, you can't really do everything from first principles. So there's some learning involved, but you still need to look at kind of the structure of the robotics problems. Language, there's a few language classes. CS224N is the kind of the standard language class. It is also ML heavy, just like CS231N. It talks about a bunch of different language tasks like parsing and translation. CS224U is called natural language understanding. People ask, like, what's the difference between processing and understanding? Historically, there used to be a bigger difference, but now with deep learning, I think these two classes have much more overlap. You can look at the topics; they're kind of slightly different. Maybe a more emphasis on semantics. There's a class on applications of virtual assistants, and next quarter, I'm actually going to be teaching understanding and developing large language models. So you might have heard me talk about foundation models or GPT-3 or things like that. Beyond just the kind of the technical aspects of how these models work and how they're built are a lot of kind of social, ethical, and legal considerations. So we're going to talk about some of those things, as well as giving you hands-on experience, giving you access to these large language models so you can kind of feel them and kind of even train some of them yourself. So it should be an exciting and interesting class. Okay, so the third category is foundations. There's many types of foundations. These are more mathematical foundations. So convex optimization, it's a great class to really kind of understand optimization. So most machine learning people these days think run SGD and that's good. And for many things that's fine. For kind of more quote unquote sloppy optimization, that's fine. There are cases where you do want to optimize your utility function, and you need to do something more serious. So optimization, and also this class is actually I took this class in a similar class in grad school, and that's really when I started kind of understanding linear algebra. So I think it's even if you're not interested in optimization, it gives you familiarity with thinking about kind of linear algebra. Statistical inference. So there's a whole host of statistics classes, which is important to kind of think about. So, machine learning and statistics have clearly a lot of overlap, but they kind of have different emphasis. Statistics focuses more on kind of scientific discovery, machine learning more on engineering. So some of the questions you might ask are different. Like you care about like hypothesis testing and confidence intervals and the validity of your inferences, because you don't always have just like a held out test set that you could, or validation set that you can measure performance against like you have in engineering. So a lot of, if you're thinking about, more like kind of scientific applications, I think a bit of rigorous statistical thinking would be healthy. And there's a class, if you ever wonder, why does it all work? Why is machine learning, deep learning, why is it so effective? You can take machine learning theory, and it talks quite in depth about the kind of fairly technical probabilistic tools like uniform convergence that helps you explain or partially explain the success of machine learning. Although, it won't answer the question why things work. There's a lot left to be understood, but it hopefully will give you at least a little bit of taste of like, oh, okay, now I understand, like, it's not just a kind of a, all heuristic. There's some kind of statistical principles behind what we're doing. Cognitive science and neuroscience are kind of other areas that feed into AI. Cognitive science, you can think about it as a software. We're thinking about the human mind. So this class talks about using probabilistic programs, remember, from the Bayesian networks modules to model human reasoning. So this is really kind of interesting. And then you can look at neuroscience, which has to do maybe more with the quote unquote hardware. I mean, this is a theoretical neuroscience class, so it's not actually going to be real, hardware, so to speak. But you ask questions like, what is the back propagation, which is the bread and butter of deep learning. Actually, the brain can't implement that because it's not a local kind of rule. So people have been interested in these questions like, what is kind of a neurally plausible approximation that kind of explains learning? So pretty interesting open question there. Okay, to summarize, so here's a type of classes, methods. So this is kind of going straight in some sense. You learn about more advanced techniques, general purpose, all good. But I would really encourage you to also think about applications of AI, especially things that you really interest you and that you're passionate about. And they really help you understand and appreciate the methods that you're learning. And do invest some time in investing in depth. And there's a lot of classes outside AI at Stanford. So definitely explore and don't limit yourself just to kind of AI classes. So just general tips, beyond taking classes, there are a lot of resources online, talks, tutorials, blog posts. It's like information rich, and you can learn a lot from just watching things online if that mode of learning works for you. Some people prefer downloading code and tinkering. A lot of stuff, thankfully, is still open source, and people release their code and tutorials. And just talk to professors and other students about what not just like what classes to take, but how they think about AI in the world, because a lot of learning is not written down in some sort of formulaic textbook. I think the field is moving so fast that I think sometimes it's just in the heads of a few people. All right, so that's the end of the second section. I'll take any questions now. So is it okay to take 230 without first taking 229? I believe the answer is yes. If anyone has taken these, feel free to chime in. I think 229, especially if you've taken 221, that should be more enough to take 230. 221 really gets you kind of you derive a lot of different learning algorithms, and think about like mixtures of Gaussians and so on, which aren't needed if you're just interested in applying deep learning. Any other questions? What would be the best way to talk to professors and other students? That is a good question. I guess ed is probably not going to be super, it's probably going to go dead after the course. I guess email is always an option. I mean, the best time to talk to a professor and other students is during the quarter when they're holding office hours and everything. But maybe after the course, some professors still have office hours. Is it okay to take 220 for N without previous experience in deep learning? 220. The short answer is yes, because I think the first, again, condition on you haven't taken 221. You have kind of the basics. 224N starts with some of the basics of deep learning, so you can get by. I think if you can take deep learning, I think that's better. I think there's always this thing where if you take the more prereqs you kind of take, then the more time you'll be able to spend kind of actually enjoying the kind of language aspect rather than, let's say, the deep learning aspect. CS221 would be offered online later. It's going to be offered in person in the winter. Nope. In the future, it's definitely a possibility. I haven't thought that far in advance, depending on how much interest there is, I guess. What are classes that would be offered remote? For that, you have to check the, so I don't know which ones are remote versus in person. I think by default, everything's going to be attempt to be in person, I think. All right. So I think that's a lull in the questions. So let me move on to the third part. Okay, so now we get to kind of step back and think about where AI as a field is going. So, if you think about where we are today in AI, I think of AlphaGo as kind of a quintessential kind of image that captures, the progress and the optimism that we're feeling today, right? Kind of a very bold effort, surprised a lot of people, experts of Go and AI, and kind of really, it was a kind of a triumph of sorts for AI and machine learning and deep learning. And you kind of see this kind of optimism kind of and boldness kind of continued with things like GPT-3, which came out last year. OpenAI released this large language model, 175 billion parameters trained on a bunch of text, and orders of magnitude larger than the previous model, and it costs something like $4 or $5 million. Billion would be a lot. And one thing that's interesting is that it's just a language model. So remember, a language model is just something that takes a context and predicts the next word. So you think about this is the world's most boring task. Like, why would you want to just predict the next word? But it turns out that if you do this at scale, you can do all sorts of other things. Like you can get it to convert natural language into SQL queries, or you can do question answering with in a dialogue format. It doesn't do any of these like particularly well, but the mere fact that now you have a single model that if that wasn't trained for these tasks, doing anything sensible is impressive. It's like, the question isn't how well the bear dances, it's like the bear is dancing at all in some ways. And this has led to a whole era of large models, which are really improving the accuracy across the board on mostly kind of language tasks for now, but you see it in vision as well. And it's kind of this optimism and progress that's really leading to AI being kind of deployed, across a countless number of different areas, from all the consumer services, like think about Facebook or Google, but also in other types of areas as well, although obviously to a lesser extent, because they don't have as much kind of AI expertise as the tech giants. And it's also being applied in even many areas like education or credit employment, which really starts to kind of affect people. But that said, like some of these AI systems are like logistic regression, not GPT-3. Many of them are actually closer to logistic regression than GPT-3, but nonetheless, this whole umbrella of using data methods to automate certain types of decision making is a general trend that encompasses many different regimes. So now, what I want to spend the last kind of lecture reflecting on is what is the societal impact of this trend. Having spent a whole quarter kind of talking about the technology. So I just want to use a simple example, machine translation. Many of you probably used it. And it's one application where just the quality of machine translation has just improved significantly due to advances in AI, and which is great. It can help break down language barriers, increase accessibility, improve the kind of productivity of the economy, and so on. And so this is generally positive. But there's always a kind of, you need to look at the kind of the flip side of things. And while they're ubiquitous, they have problems. So for example, Hungarian is a language that doesn't distinguish between female and male third person pronouns. So when you translate into English, it has to guess what the gender of the pronoun is. And you can see that it patterns very stereotypically along kind of professional stereotypes. And these kind of biases are, sometimes if you don't bother to think about it, maybe don't seem to raise an alarm. But I think these are actually kind of the frog getting butter alive kind of setting where it starts kind of creeping insidiously throughout society and it gets amplified. So it's something really to be careful of. There's also weirder stuff. So there's this kind of one example from a few years ago where in some Maori, which is I guess a language that doesn't have that much data, you type in some nonsense, dog, 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 and you get some really disturbing stuff coming out. And no one really knows why this is kind of happening. I think many of these issues are due to the fact that machine learning thrives on these complex models fitting spurious or fitting correlations in data. So it's like we're kind of pushing the limits of what we can do. And that's kind of the kind of outlook I think the field has had for quite some time. I mean, you have to remember that even 10 years ago, like computer vision basically didn't work. And so people were like really for decades trying to get things to work at all. And now things work. Well, now we have other things to worry about. So I want to highlight something called spurious correlations, which I think is, a cautionary tale. So here's a task. It's a pretty solid task. You take an X-ray image of a chest, and you're trying to predict whether there's a collapsed lung or not. And if you take a standard, computer vision machinery, this works pretty well. But take a closer look at this this image. See that tube coming out here? That's called a chest drain, and it's something it's a common treatment for collapsed lungs. Okay, so and it turns out that this is one of the signals that the model is picking up on. So it looks like, hey, this person was treated for collapsed lung, therefore, he has a collapsed lung. Okay, so if you look at the accuracies, the AUC of here is the set of the entire population. Here are the people who have gotten chest drains. You're predicting on them much more accurately than the people without chest drains. So you might seem like, oh, okay, we're doing pretty well. But actually, for a segment of the population that doesn't have chest drains, you're doing actually pretty, not so well. And this is exactly the subpopulation of untreated patients that you actually care about, because if they already have a chest drain, like you don't need to predict whether they have a collapsed lung or not. So this kind of is a cautionary tale that you really need to not just look at the accuracy, but kind of really understand how the model is actually making that prediction, because if it's just latching onto spurious correlations and you go deploy this, it might not be so good. Here's another example. Suppose you're trying to figure out the effect of a treatment on survival of patients. So here, maybe you did some study, and here's the data. So for untreated patients, 80% survive, and for treated patients, 30% survive. So the question is, does the treatment help? So how many people think it helps? So maybe raise your hand if you think it, doesn't help, or just put something into the chat. That's fine too. I'm trying to make this a little bit interactive, get people to think. Doesn't help. That's possible. Unclear whether it helps. Yeah, who knows? It's right. If you're very naive about it, you can think like, oh, okay, well, it's correlated. Survival is correlated with not treating. But exactly. Sick people are more likely to undergo treatment. So there's a hidden confounder here, which is how sick you are. So this doesn't tell you anything. So if you're just doing machine learning naively, you could really be doing completely the wrong thing. And there's this whole field of causal inference, which provides kind of rigorous machinery to help you answer these kind of questions. And especially kind of in these kind of high stakes medical settings where there's maybe not lack of data and lack of ground truth, you really, really need to be careful, right? Like for machine translation, you kind of can get a human to look at the sentence like, yeah, seems reasonable. And this is kind of the more typical engineering attitude. Like I try it and I can always validate you if it works. Like when you can validate when it works, yeah, maybe it's okay to use something that you maybe don't fully understand. But like when you have to rely on, when there's no validation, I think you have to lean much more on kind of first principles. Okay, so cautionary tale is always be aware of the limitations of a technology, and machine learning definitely has a lot of limitations. And I think it's really important that you walk away with this class not thinking like, oh yes, machine learning, now I know how to do SGD, I get a data set and I can just go with it. You have to be aware of the limitations. All right, so now the second part of this kind of module, I'm going to talk about AI ethics. So many of you probably have heard the term AI ethics kind of thrown around. It's often in the news. It's often kind of, there's a lot of heat kind of around this term, like ethics. People are not being ethical, and what's going on here. And at the broadest level, it's about how we ensure that AI is developed to benefit society and not harm society. Okay, so sounds easy, not easy, but like uncontroversial, right? And there's a lot of principles, and people have written a lot about this. So I'm not an ethicist, so I can't speak to this kind of in great depth, but starting with the kind of the Belmont report from the 1979 on human subject research, and there's an ACM code of ethics, and all these companies are now putting on our kind of responsible AI principles and so on. It seems like there's a lot of guidelines, which is good. Often these things say like, respect persons, don't do harm to people, and which you look at and you say, okay, well, yeah, I don't want to harm people. But the real question is like, how do these high-level principles relate to the concrete actions you take? Because a lot of these ethical issues aren't about like any malice or misguided kind of intent. It's really about kind of has to do with kind of ignorance. If you're not aware of something, then bad things can happen even if you're not aware of something. Okay, so what I'm going to do is walk through a few specific considerations, which has to do with kind of this umbrella, AI ethics, which hopefully gives you a bit more kind of concrete guidance. So there's the considerations are data. There's what objectives you optimize. There's inequality, which we've talked about before. Idea of harmful applications, which I'm going to get some, a survey of people, so get ready for that. And then automation versus augmentation. All right, so moving on. So data. So AI is largely powered by machine learning. And without data, there's no machine learning. So we must naturally ask the question, like, what is this data that we're talking about? So here's an example. There's this data set called Tiny Images, 80 million images, which has been used since 2006 in the computer vision community. And it was actually taken down because it was found to have various kind of offensive content in it. Even ImageNet had some of these kind of objectionable issues, and it was kind of cleaned up afterwards. So a lot of the times AI systems are relying on web scrape data, and we know sometimes on the web it's not a pretty place, and if you're just scraping data and not really carefully looking at it, you can kind of inherit a lot of these kind of offensive material. Second of all, there are historical biases inherent in data. So kind of social biases with race and gender, even if they're not offensive, the idea that, maybe the lack of representation of certain kind of marginalized populations is itself kind of a problem. So you have kind of two types of problems. One is you can represent people or badly, or you cannot represent them, and both are, things to worry about. So there's another maybe thing that people don't normally think about when it comes to data, which is that should a piece of data, let's say I go on a vacation and I take a picture of my dog, and I post it on Flickr, and then some big tech company scrapes it and then does some pre-training and uses it to do some scene classification. Is this good? Or should it be allowed, right? And right now, I think we're kind of pretty laissez-faire about this, where internet scrapes are kind of the norm, and there's no consent here. There's maybe, a lot of things are copyright, and I'm sure there's tons of copyright, potential copyright violations. So this kind of begs the question, like, data is produced by people for doing certain activities, right? I post an article, I write a book, I send messages to people, and machine learning is something that kind of sits on top and kind of siphons that data for usually another purpose. And the question is, what right do I have to say, like, no, that should be allowed or not allowed? And often this kind of goes without even users being aware of what's happening. So another piece of data that is important is how much work it takes to produce it. So often we think about technology and machine learning methods, because that's kind of, from a computer science perspective, that's kind of the object of study. But more and more, I think it's important to be aware that data takes, what's powering all of these things, right? Like, you think of AI as reducing human labor, it makes things more efficient, and so on. But it's not free, and it requires resources. So this is an excellent book by Mary Gray and Sadigh called Ghost Work, that kind of documents the amount of kind of human labor, usually crowdsourcing, that's used to create data sets or moderate flag content that is used to power these AI systems. So a lot of AI systems have the kind of a veneer of being like automated, but really they're kind of being powered by people at some level. As a kind of one example I want to point out, which is good food for thought, is in machine learning we like to think about the distinction between label data, which is really expensive to obtain because you have to like pay people to label it, and unlabeled data, which is cheap or even free, right? But if you think about it, if you go back to what I said about data is created by people expending capital, right? Think about like quote unquote raw text, books and articles. It's free because, we just took someone else's book that they spent a whole year writing, and we didn't pay them for it, right? That's why it's free. And so it's kind of important to kind of keep that perspective that, a lot of machine learning is kind of deriving value from, the labor of people who are not getting compensated, for the asset. So, just a little bit of perspective. All right, so the second topic is objectives. So optimization is largely touted in this class. It's a powerful paradigm. It allows you to express a desire in the form of an objective function, and then separate that from the intense resources and algorithms to make it kind of come true. You make a wish, and then you can get it to come true. That's the kind of the power of optimization. But the question is, what should the objective be, right? Ideally, it would be something like happiness or productivity, but usually these things are impossible to measure. So often we have surrogates for them. And so, okay, now we're not getting the thing we actually care about because their surrogates are approximations. And furthermore, there's kind of different incentives, right? Businesses are always incentivized to maximize, profit. Nothing against them. That's what they're designed to do. and that's not always aligned with kind of what's the benefit for the the social good. And so just an example, most internet companies use clicks or views as a major component of their objective function. Why? Because it's the signal that they have, and it's really good at driving up kind of profit. And usually, it's actually it does reasonable things. It gives you what you say you want. But obviously, what people's reflexive actions are at any given time are not necessarily representative of their long-term goals. And moreover, at societal level, we see that this leads to potentially big problems like polarization, which is a whole nother topic that I won't get into. So I think it's always important to think about like what the objectives that you've kind of set out to be, and beware of any sort of surrogates or misaligned incentives. Inequality, we've talked about kind of in machine learning lecture where, remember the gender shades, a project where different gender kind of image recognizers work differently on different populations of people. What do you do about this? Well, you can collect more data for certain types of groups, but often this is hard to do and more expensive. So there might not be kind of incentives to do this unless there's regulation. One solution is data. The second solution is in the methods. We looked at how you can minimize the maximum group loss using group TRO, and you can mitigate some of these performance disparities. Of course, it's a big philosophical question, like what kind of trade-offs you want to take, which you've had the opportunity to kind of reflect on in the homework. But one thing I want to mention is the idea of auditing. Auditing, I think, is a really powerful force because a lot of systems, especially commercial systems, you don't really know what's going on in them, right? And in the gender shades example, after the study came out, companies were incentivized to fix the problem, and after a period of time, disparities were largely vanished. So just like by the mere fact of studying what systems are doing can actually sometimes be enough to incentivize companies to take action. Okay, so now I'm going to do a little bit of an audience participation. So get ready to kind of raise your hands. So there's a question of what applications are ethically okay. Okay, so this is going to be interesting. And moreover, when a researcher makes a kind of an advance, how do you assess its potential harms? Okay, so here's one. Autonomous weapon systems powered by AI that can track objects and fire missiles or whatever. So maybe you can vote either up if you think this is a okay application, or a down if you think this is a not okay application. Okay, so I think most people who voted say no, if not all. Okay, so this should be an easy case. I don't know what everyone else thinks. Hopefully this should be okay. So maybe there's some I think you could maybe make a case for this, but I think this is largely in the community regarded as like very, very ethically problematic at the very least.
Yeah. So I wrote yes for defensive role because I was thinking like if just like there was an attack and the Israeli autonomous system were able to defend missiles and that protected a lot of people, then in that perspective it might be good to have an autonomous system, but in general that.
Yeah. So I'm not going to get into the kind of detailed argument. I think you can debate these things for a long time, but I think I'm trying to kind of bring together a spectrum. So I think this is one example which most people think is very problematic. So what about deepfakes? So again, vote. How many of you think this is okay technology versus not okay? So, they have genuine use cases, maybe in entertainment, like if you want to create like an avatar or something, or pretend you're a celebrity. But on the other hand, of course, as this picture points out, you can fake, Barack Obama or some head of state into doctoring a video that gets them to say, anything. So obviously, this is potentially pretty problematic from a point of view of disinformation, where people can't tell what's fact and what's fiction. So what about image generation? Okay, so this gets a little bit more interesting. So suppose you're not generating Barack Obama, you're just generating cute puppies. Okay, how many of you think this is okay now? Cute puppies, yeah. Okay, who doesn't want more cute puppies? Okay, so more yeses, but intuitively it feels like it should be okay because you've kind of distanced yourself from any sort of weaponry. But the truth is that a lot of the methods that you see is actually general purpose, right? Like if you can generate cute puppies, you can generate Barack Obama, right? So this is where I think the ethical dilemma comes about, which is this idea of dual purpose technology, right? The same technology can be used for putting a smile on your face or spreading disinformation. And there's no, I'm not going to offer any solution even if there were a solution, but this is something that needs to be kind of just the process of thinking about this while you're doing AI is extremely important. And you can even go farther and say, what about deep learning? Okay, so maybe most people would say, yeah, deep learning is probably fine because there's so many good things you can do with it. But some people would argue that the idea of developing technology that enables large organizations to, amass data and, have centralized power and all that is, inherently evil. So you could take that position as well. So there's no, right or wrong answer here. But I think there's just a spectrum of viewpoints, and I think a lot of the AI ethics is this process of debate and reflection, as opposed to it should not be like, here are the principles. If you just follow them, then you get a stamp of approval. It's not like that at all. It's about like internalizing these questions and carrying them with you at all times. Okay, so the final thing I want to talk about is automation versus augmentation. So AI is, you see a lot in the news like, oh, AI is dangerous because it can replace jobs, or you may think about like an AI that goes rogue. And I think a lot of this, whether it be kind of a real worry or not, has to do with the framing itself. Ever since the beginning and the inception of AI, there's this idea of an agent that is supposed to be intelligence, or wanted to be intelligence, and it can do things in the world, right? And once you call it an agent, that means it has agency. That means it can do things that are, it's its kind of own entity in some sense. And if you frame it like that, then now you're just fighting an uphill battle to coax it to be aligned with human values. And it's like, wait, no, I didn't mean that. Let's get it to do what we want. And this is so deeply ingrained in the framing of AI, from things like the Turing test, which is about an agent that can actually deceive a human being, for what it's worth. RL agents that kind of are autonomous and doing their things, and the whole idea of Gen AI, artificial general intelligence. And this leads kind of to a very, explicit kind of automation perspective, because, well, you have an agent, it's doing things. Now it's going to, do the thing that the human was doing. No, if you go back to the 1950s, there was another kind of line of thinking, which is interesting, called IA. intelligence augmentation or amplification, which was about creating tools that help humans. And this is kind of in some ways like kind of a predecessor of HCI, human computer interaction, which focuses on the augmentation of human abilities. So now this in some ways I think is more amenable to I think this perspective allows us to kind of sidestep a lot of these kind of problems, because baked into the premise of IA is like we are trying to make humans smarter or faster or whatever, and it's human centric as opposed to kind of agent centric. So a lot of these kind of interesting AI moonshots like the Turing test or agent that can play chess would not have pursued under kind of an IA agenda. And it's clear today that AI has, by focusing on the agent perspective, it has led to a lot of powerful technology. But it's also clear that we need a lot more kind of IA thinking to help shape this technology, because fundamentally we should be developing AI to improve the human condition. Okay, so this is the final slide. So AI is a technology, and like most powerful technologies, it's a dual use technology, which means that it can improve efficiency, accessibility, productivity, dare I say happiness, I don't know. It can do a lot of good things, but it can also do a lot of damage. It can be explicitly used to harm people. But even putting that aside, I think even by virtue of not being cognizant of certain issues, it can exacerbate social inequalities. It can do harms without people thinking about it, which is why I want to kind of stress so much the idea of just being aware of these issues. I think is kind of half the battle in terms of making progress here. And the final takeaway is, just because you can build something doesn't mean necessarily that you should. Maybe you should, maybe you shouldn't. You should always ask yourself, what are the benefits and what are the risks? And this might mean sometimes slowing down and challenging the status quo, which is uncomfortable because we're used to thinking about charging ahead and march, in the march of progress. And there aren't any easy answers, but I think really mindful deliberation can go a long way here in making AI more ethical. All right, so that is the end of the lecture. Hopefully you guys learned a lot, and hopefully this was good food for thought. Please give feedback on course evaluation on Access, and thanks for an exciting quarter. All right, I think we have a bit of time for questions.
Actually, I had a question. More to hear your thoughts about so the slide that you had regarding the deep fake and then picture generation, things like that. So I feel like a while ago, if you want to verify something, you find out about something, you read it up from a verifiable source on the internet, and then it was like if you have a video of a person talking, that's more reliable because content you can't trust. But now deepfake videos are not so reliable anymore. So a sense of an erosion of verifiable truth in digital content. For this, what you might be, what your thoughts may be on that.
Yeah, I mean, everything you said is true. We can't really trust what we see online. I mean, this is going to be even more true kind of going into the future. I don't think all hope is lost. That just means we need to kind of reset our expectations and have other mechanisms for, validation. And, I think that, I think maybe there are non-AI things you could attempt to do. For example, authentication of, provenance of like, oh, okay, this video or this image or this text was actually produced by this, entity at this particular time and place, and it was certified and you have to design a kind of a secure mechanism for authenticating. So this is more in the kind of realm of security. But another example is Photoshop exists, and I think we're all okay. I think we maybe, video might be a little bit more kind of visceral in some sense, but routinely there's images that can easily be photoshopped with high fidelity, and we don't necessarily trust those. So I think I guess I'm trying to not avoid sounding too pessimistic about the future, that there are things we can do, but we do need to do them. And I think that when developing AI technology, it's going to happen eventually. I think most of this is kind of just buying us time, right? Until and kind of slowing things down enough so that we have time to react. I think in 20 years, I don't think there's any way no way you can stop people from having deep fakes. It's much earlier than 20 years, but just to give a upper bound.
Thank you. Thanks.
Excuse me, Professor. As AI becomes more democratic, like more and more people can practice AI, then will it become like less and less harmful in the longer run? Just like more, like if everyone in the world can train their model, then will it become less harmful?
Not necessarily. I think I don't like using an analogy, but like if you imagine everyone can build a nuke in their backyard, doesn't mean that things are better. And it could just lead to an arms race between attackers and defenders as well. Whoever has the most powerful model can kind of win. It's really interesting because I've been such a big proponent of like transparency and openness, and in research you just put everything out, right? You're supposed to. That's kind of the whole idea of science. But sometimes there are technologies, and there's a situation where maybe it can do harm.
Sure. Thank you. And one more question. Throughout the course, and there also have been some talks like AI cannot still learn common sense. So, do you have any pointers, any reflections as to how to learn common sense in AI?
Yeah. One question is what constitutes common sense. There has been a bunch of work in common sense reasoning in the last 5 years. Yejin Choi, as a professor at University of Washington, has done a lot of excellent work in this area. Used to be like common sense reasoning was talked about, before machine learning, and people didn't really work on it, but now it's kind of coming back. But it's tricky. It's really a slippery concept. What constitutes common sense and how you get your hand around it.
Sure. Thank you. Thank you.
Any other questions?
So, Professor, what are some good sources to know what is latest happening in AI industry?
What is the latest happening in AI industry?
Yes. So in different fields. So what is the new technology coming up for the application to build on?
You're asking just generally what So you're asking for references where you can find out about how to keep up with the latest AI, or you're asking what I yeah, I don't know if there's a definitive source. Archive, I guess, provides is a feed of the latest papers, often blog posts or Twitter. People post a lot of kind of recent advances there. I guess social media is, for lack of better, concrete description.
Okay, thank you.
I mean, I would say that it is a very biased, sample. It's the things that are generally done in research, done in like kind of prominent, research labs. I think, which is good. I mean, I think it's follow other ML researchers on Twitter. That's how you learn about stuff. I think there's also a lot of AI that's in the kind of private organizations where people aren't publishing, and there can be hard to figure out what's going on.
Sure, thank you.
Yep. Anything else? Why do people publish models even if they are expensive? There are, I think, multiple reasons. Publishing models allows other people to build on top of work, so it's good for the community to have more, sharing. You can make progress faster. Also, you get recognition more on a kind of selfish note if other people built on top of your work. That's kind of the academic, model in some sense. Okay, well, if there's nothing else, then let's end there. Thanks everyone again for coming to the last lecture. After a whole quarter of modules, I guess it's kind of nice to get a little bit of live interaction, although I guess I've seen many of you at the faculty chats, so that's been nice. But yeah, good luck with the rest of your quarter, and see you next time.